aye, Captain.
Ooh. It is a red line.
We ready?
Define ready.
Are we ready?
Yeah.
I'm ready. All right.
Subjective.
So we got the small engine dynamometer team. Now I'll let them introduce themselves and we'll get started right at 6 o'clock. So vote for 15. And then 5 minutes of Q&A when they're done. 20 minutes cycle time.
Ready, boys?
All right.
Alright. Hi, I'm Wyland LaRose.
I'm Andrew Jennings.
And I'm Colin Jansel.
Jaden Matt.
And today we'll be presenting on our small engine dynamometer. So some background on this project is that the NMU Baja Racing team was looking for a device to test their engines with. They wanted something to let them know if they needed to repair the engine and assess engine performance for their cars. So we set out to build that. Some design targets we spec for this was, first one was we wanted it to be relatively low cost, as if this project ended up being the same price as a commercially available product out there, then why wouldn't the NMU Baja team just buy that said product? So we set out to make it far cheaper than that. Another issue we had was that we needed to make this relatively small too, as the Baja shop over there doesn't have much room, so we set out to make it under 6 square feet. The NMU Baja team's engines are all between 5 and 15 horsepower, so we needed to make sure we can measure between that range as well. For accuracy's sake, we set out to make sure we could measure between a tenth of a horsepower. It needed to be easily movable and safe because we run the engines outside and not in the shop. Needless to say, it also needed to be safe, as we didn't want anyone to be getting hurt. And last but not least, it needed to be serviceable with shelf components. What this means is that if a washer or nut broke, we can go down to Menards or Lowe's and pick up new components to replace the ones that failed.
So this is our general design overview. Some of you have already seen this before, but you can see our engine to be tested, power and fluid loop here. We have 2 pressure transducers and a throttling valve to basically increase or hit a targeted pressure in the system. By measuring that pressure and utilizing the general energy equation for fluid flow, we're able to measure the power added to the fluid by the pump, and combining that with the mechanical efficiency of the pump, we can find the power required by that pump and therefore the load on the motor. This is our SolidWorks model, just basic, showing our adjustable engine mount, and then just using this to get a general layout what the table was going to look like. Some of the techniques and considerations we made here, we used various decision matrices, considering the targets previously discussed, or design targets, and analyzing various different options of a dynamometer, whether it be a purchasable product or the different types of dynamometer that it would be possible to build. We utilize these decision matrices to come to the decision of a fluid flow or fluid friction dynamometer. We utilize fluid analysis. You can see just some general numbers here. With a set pump displacement, a set pipe diameter, and targeted pressure, we can output a range of expected power requirements for the pump at various RPMs. So this is what we would expect to see with a 2000 psi pressure drop at about 3800 RPM would be about 0.9 or 9 or 8 horsepower required by the pump. This is our build here. You can see here with the engine to be tested, all hooked up to the fluid loop. It's hard to see behind the engine here. Hooked up with a belt and pulley system, and then our adjustable mounting system here to allow us to mount different motors and engines. That made it easy for testing. We do have some extra supports under the table. You can see it's all made out of wood. This is to increase the rigidity of the tabletop, so the gasoline engine wouldn't vibrate the entire system and make things fall off the table. This was our testing setup with 5 horsepower motor that we utilized, that we can provide a known load to the system or a known horsepower to the system and run it at that load to hopefully verify the numbers based on that we're finding from our program and our fluid loop.
And this is our LabVIEW program. It is going to be taking all of the data from our various sensors and then running it through the back end on the right there and outputting 3 different graphs, one for horsepower, torque, and RPM. And the front panel on the left is what the user will be interacting with. And other than those graphs, it also has 2 indicator lights for safety reasons. The first is an overpressure indicator. This is to prevent a blowout of the system that will both protect the user and the pressure transducers. Then there's also an overspeed indicator, which will protect the pump from going over its rated speed. And then above that are numerical indicators, which are showing some of the values in the back end, so that way we can, in real time, check to make sure the values in the back end are matching what we're expecting to see that we calculated previously. And then for our test setup and procedure, we mounted the different motor that we were trying to find or trying to test, and we started the LabVIEW program. We allowed the motor to run for a moment at the RPM we were trying to target to allow the system to reach steady state flow. And then we started slowly closing the restriction valve until the desired pressure was built. Unfortunately, with our initial testing, we were unable to get the pressure we were expecting with the pump that we initially spec'd. Our flow regulator valve was operating more as an on-off valve than as a variable valve. We then switched to a higher speed motor, or a higher displacement pump rather, sorry. And we ran it with the gasoline motor at first. And when we ran that, we were getting measurements that were about 1/10 of what we were expecting to see. So if we were running at where we'd expect to see 9 horsepower, we were seeing 0.9 horsepower. In order to check if this was a error on our end or if we're off just by a factor of 10 somewhere, we test it with a known input of the electric motor, which is the LabVIEW that you can see here on the left. Now in this run, we started the system, got it up to rated speed, which was about 1750 RPM, and then let it hit steady flow and started slowly closing the valve. We would close the valve and we were able to build up to about 78 PSI. But then at about halfway, as we were closing the valve, we were no longer building pressure by closing the valve. And we ended up closing the valve entirely. This, of course, led to the pump stalling out nearly instantaneously and causing the system to fail, which you can see in the graphs there. There's just that immediate drop. And unfortunately, this happened on Sunday, so we have had to make some design adjustments. And the first adjustment we're going to make is we're going to start targeting a higher pressure. And although this is a little bit counterintuitive, we did further calculations and found that with a higher pressure, we would be able to use the same pump that we were using and be able to vary the flow more accurately. However, because of the higher pressure, there are some safety concerns that obviously come with that. And so we looked into a new valve as well as a pressure relief valve that would allow the system to get up to pressure safely without either blowing out the sensors or causing failure somewhere else, hurting the user.
So to get this fluid friction dynamometer to Baja, further testing with the new pump is going to be needed to be done, and it will need to be done at higher pressures. The testing will utilize new calculations that have been calculated, that have been made, and predict that a high enough pressure could produce the power required, power needed to sufficiently measure engine power. Baja will be provided with a technical report and current findings on how to proceed further with this project. The fluid friction dynamometer, as spec'd, has reduced the cost of the off-the-shelf option from Go Power by about 75%. This cost could be further reduced through bulk purchasing and streamlined manufacturing. And if this dynamometer were made into a commercially available option, it would come in the form of a parts kit, and then the user would manually assemble that themselves. And then for our stated problem, our solution is a fluid friction dynamometer that will output torque, horsepower, and RPM. With our current setup, the small engine is working. However, our previous calculations showed a resolution off by a factor of 10, as stated previously by Colin. Our team hasn't strayed far away from the original design. This was our original design shown by Andrew. And then this is our current design, also shown by Andrew. You can see there's near no difference. The only differences that we have made are component changes, and those are mainly just to make the design better and just have a better outcome overall. And then we want to, excuse me, what happened?
Space again on the last slide. It's fine. Just take it on together.
Give me 1 second, just close out for no reason.
Don't hit it too much. There you go.
There we go. Sorry about that. I'd like to thank all of the NMU Engineering Technology Department, all of our faculty members, for help and advice. Excuse me. We want to thank all in the NMU Engineering Technology Department with help and advice provided in our project. We also want to thank NMU SAE Baja team for the space, tools, and also extra help provided. Are there any questions? No?
Well, you're not off the hook yet.
So you guys,
So, what's your plan going forward?
we want to test at higher pressures. Right now, we're operating at a maximum pressure about 200, 250 psi. At that flow rate, or at that pressure with the flow rate pump that we have, we're only achieving about 9/10 of a horsepower power requirement by the pump. And our new goal right now is to hopefully increase flow rate just a little bit with a slightly larger pump and increase pressure in order to achieve we want to hit a power requirement of the pump that's similar to the rated power output of the motor at the given RPM. That way, if the pump requires 13 horsepower at 3,800 RPM, the motor outputs 13 horsepower at 3,800 RPM. That should sufficiently load the motor. We can actually notice a difference in the motor operation and measure the power output of the motor.
So what components do we need to proceed?
So right here is a combined flow restriction and pressure relief valve. That would be one of our main components, as well as a new pressure transducer. Our current high side pressure transducer only measures 500 psi. It's rated, its burst pressure is about 6,000, but it won't measure any more than 500, so we need to switch that up for a 2,000 or 3,000 psi pressure transducer, as well as a couple of extra fluid fittings to integrate this pressure relief valve into the system properly, so we have an actual relief loop to feed back into the tank. Those would be the main components. We hope to be able to do it with the current motor we have right here, but that's about 1/3 of a cubic inch per revolution in displacement. And in our current calculations at 2,000 RPM, right here, I don't know how visible that is, but we only achieve, sorry, it's not 2,000 RPM, sorry. Even at 4,000 RPM, we only achieve about 8 horsepower required by that pump. So we have an Excel spreadsheet that we've just been kind of speccing different parts by changing the displacement here. We found we would need about 2/3 of a cubic inch per revolution minimum to meet that target for 2,000 PSI to hit a 10 horsepower pump. Otherwise, if we go a little bit higher, we can increase that horsepower requirement just a little bit and hopefully increase our testable range.
Would you guys say that in retrospect was a calculation error or component selection or both?
Component selection, I would say. We had sort of two trains of thought at the beginning of this project that typically one consideration we made is if you have a pump that only requires 1 horsepower, you have a 10 horsepower motor, you're never going to properly load that motor. But at the same time, we were also thinking that technically shouldn't matter if we can close the fluid loop and build the sufficient amount of pressure, then it should still load the motor. That turned out not to be the case, as when we did that with the electric motor specifically, the electric motor did not care, and it just overpowered the pump and started skipping the belt off the, so it was a pretty interesting system failure. Thankfully, no damage to anything, but it was a fun test, I'll say.
How much have you spent and what was your anticipated cost?
Our anticipated cost, we were hoping to be about $1,500 to $2,000.
Yep.
And right now we're sitting around 2,300, is that right?
Correct.
Yeah, 23 to 25. That's still a quarter of the cost of a fluid water brake dynamometer would be the most readily available option from Go Power Systems. Their system for a full test and data collection setup is about $10,000 for a small engine dynamometer. And so we're still well underneath that, even with new components.
As spec'd, this would be about $1,600. Our original goal would be about $1,600, but with new components, it did end up being about $2,300.
Yes.
Other questions? All right, nice job. There are chairs in the other room if you want to bring them in. I've got a seat. I'll take that. It's in the front row. Handful. Who would like to do a career evaluation? Any of our casual visitors? Change your mic, yeah. I can actually get something reading. Alright, so we'll just try to stay on schedule, so we'll go with 20 after. We now have chairs. You have a joke? Joe has a joke for everyone while we Joe has a good humor. And a really advanced filter for some of his Everyone looks really sharp, by the way.
everybody. I'm Madison. This is Carson and Joe. Our project for this semester was to design a tensioning device for Able's inline cable system that is single use and able to be sterile packed. Okay. Some background on this project. Able already has a device that exists, but this product is not on the market due to its overall cost and size. You can see here on the left side that it requires another device to operate, not made by Able. So the goal for this project is to eliminate that device. This device also requires to be disassembled after surgeries and sterilized in between each use, whereas our product would not. This is our final prototype here. You can see that there is a star-shaped knob that attaches to a collet, a tensioner, a cannulated driver that runs to the center, and jaws, and a body. The body depicted here is in white and is split in half to allow access to the gears and tensioner that are located in the center. Here's a demo video of us operating the device. Here you can see the device is attached to a cable that runs all the way through the device. Here Joe is tightening a collet at the end. Tightening of this collet allows for the cable to have tension applied. Here the triangular knob is rotating and that applies tension, pulling the cable, cinching it to the bone. He's then rotating the gear so that the collet inside of the implant can rotate and locking the device onto the bone. He's then loosening the end of the collet so that the cable can come free from the device. There are three important interfaces of our design. On the right side, or on the far side, you can see a collet with a star knob. The star knob tightens down and tightening the collet onto the cable. In the middle, you can see the inside of the assembly where the gears and the tensioner are located. And on the far side, you can see where the implant attaches to the device. It attaches with two dimples on either side of the implant and two teeth that attach to the implant. As far as status, this project is a proof of concept. We set out to achieve these three goals. The jaws hold to the implant, the cable cinches to the bone, and the driver rotates to lock the implant. As far as project management goes, we set out to make 3 prototypes for this project. We did make 3 prototypes. Prototype 2 took us a little longer than expected due to some tolerancing issues we had with the 3D resin printers. These printers hadn't been tested before, so we tested what their tolerance capabilities were along the way, which required a few more prints than expected.
So our design process, a lot of the tools that we utilized were not so much math and software, but rather person-to-person communication and teamwork. We utilized a lot of administration and organization work in order to keep our stuff straightforward. We had issues communicating what parts we were working on with each other, so we ended up creating a spreadsheet that was kept up to date to communicate what exactly we were working on and what adjustments that we were working on with it. Another thing that we utilized was the printers, the filament and resin printers. The filament printer is at Able, and then we obviously use the resin printers that are here at Northern. We ended up doing simultaneous prints, so we had printed the body previously pictured, was printed with the filament printer, and then all of the gray pieces are resin printed. We printed things simultaneously and did multiple prints in order to have basically an insurance policy on whether or not stuff would actually work. And we were struggling a lot with our tolerancing, so we kind of needed to do a lot of prints. But it all ended up working out. We utilized SolidWorks simulation as well for certain features to test. Specifically what we were worried about was the jaws at the end of the device that when you apply the torque to the cable, we were worried about that twisting. something that we ended up utilizing was a collar. It's just a piece of cut PVC pipe that we put over the jaws to increase rigidity of those jaws. We aren't too worried about it. If this were to be an injection molded piece, it would probably be stronger than the resin printing, so we wanted to make sure that we didn't break our prototypes, so we ended up utilizing that collar in some cases. So here we have some analyses of different loading situations. On the right-hand side, or your left, sorry, your left-hand side, that is the red in the middle is the maximum deformation, that is 0.83 millimeters. The torque applied, even though those purple arrows are only pictured at the end, they actually go through that entire jaw system. This was to simulate the fact that while the implant itself is being held in place and can rotate a little bit, it can't move back and forth. So we wanted to be sure that we were applying a proper contact situation, so I ended up putting a contact relationship between the teeth of the jaws themselves and the little dimples where the teeth go into. The right-hand image shows the same thing, just with a collar on it. So I just basically increased the rigidity of those two phalanges, and then the deformation was A, greatly reduced, and B, translocated all the way to the end of the jaws where the torque actually is. A couple other things that we did, there's a key in the driver. We calculated how far or how big of a key we would need for that. It ended up being like 3/8 of an inch, and the gear overall length was a little over 1/2 inch, so we weren't too worried about having to get a different set of gears than we had already ordered, because that would suck. And we ended up milling into those gears at Able, thankfully, because otherwise we would have had to do that by hand. A couple other things that were analysis concerns were the travel length of the tensioning screw. We were kind of worried that it wouldn't apply enough tension with how little travel it has, but it ended up doing just fine. In the video, if you recall, I only twisted it a couple of times in order to apply appropriate tension to that cable in order for it to be tightened and loosened.
For fabrication of the prototype and the assembly, we ended up using 4 total materials, 2 of these being the resin and the ABS plastic, and then also 6061 aluminum for our collet, and then 17-4 stainless steel, which is a cannulated stock that allows the cable to run all the way through the device. This stainless steel is medical grade, so it's able to go into the body as it would be part that would go into the body when it attaches to the implant. We created a grooved slots for the assembly. This was between the 2 body pieces and the jaws. This allowed them to attach nicely together. We would also be using an epoxy to assemble this to get it to stay completely together. These groove slots just create an area for that epoxy. We also used the epoxy to attach the aluminum collet to our plastic tensioning piece. This created a strong enough bond that it wouldn't come apart when we were applying tension and tightening down our collet. So the previous model prototype was around $1,300 to produce and make, so we really focused on keeping those prototype costs down. So with this is why we focused on 3D printed parts. As you can see in the table, by using 3D printed parts, that accounted for about half the cost, while the other half of the cost was either purchased parts or metal components. If we had used all metal components, the cost would have been much higher. So by using our 3D printed plastic, which would also translate to what would be injection molded if it were to go into production, we were able to keep costs down. Our results from this project, we were able to have the device successfully attach to the implant and tighten the system down to the bone without it rotating or moving from side to side. This was our main goal. What accumulated to that was the device successfully gripping onto the cable to keep it from moving back and forth. This was done by the collet. And then also making sure that the device can attach and detach from the implant several times in case, for whatever reason, it would need to be taken off and put back on. We don't want this, we didn't want this device breaking off inside the body. Going forward, we would allow, we would recommend that there be more travel added to the tensioning thread. When we were running other tests, there were some times where we didn't have enough tension travel. Between users, everyone has different strengths, so having a longer tensioning thread would help to accommodate for that. We would also recommend a stronger plastic for the jaws. This would more than likely be taken care of when it would go into injection molded plastic, as they would be able to have a wider range of materials to choose from, whereas we only had 2 for this project. And then also adding a relative scale to the tensioning threads. We didn't do this for this prototype as we did not have time, but this is a relative scale, so there's no, there's not a certain amount of tension that has to be applied. It just has to be tight enough that it doesn't move on the bone.
So to pitch this to you guys, the advantages of this design is that it is a single-use sterile packed device. The advantages of this is that it's readily available. So the type of surgery that this device would be used for is a trauma surgery, and that generally is not planned. If the doctors are able to just have something on the shelf that they can grab and utilize very quickly, that's excellent and an advantage. Most of our parts were made out of plastic, which made it lighter and both cheaper to make. We also kind of consolidated all of the operations that it does so that it's a little bit easier to handle. Going forward, if this were to be a ready-to-be produced part, we would recommend doing injection molded parts because that'll be both quick and relatively cheap to produce a high yield. As we've mentioned several times, it would increase the overall strength of the design, so we probably wouldn't worry too much about those jaws splaying out at all. It was really mostly a concern with the prototype material that we have to use. Another advantage of this design is that it's ergonomic and simple. You just twist stuff a couple of times around and it's tightened around the bone and ready to go. Generally, we wanted this to be able to be used, like picked up and used, so we wanted to make sure that it had as little detail as possible, and I think we achieved that relatively well. So in conclusion, some stuff that we learned was a lot of tolerancing. Between all of our 3D printed prototypes, we struggled with tolerancing quite a bit. We ended up making some blocks that Professor Ruthier is going to use in the future to demonstrate different tolerancing for any class that he uses 3D printing in. We also learned a little bit about medical standards concerning what's called an externally communicating device, which just means that it goes into the body and contacts some tissue, be that bone, blood, or the interior of a artery or a blood contacted surface. And then different plastics as well. We learned pretty early on that we needed to figure out our part naming system and organization system as well, because due to the fact that we don't have the ability to have like a cloud share on SolidWorks, we aren't working on the same thing generally, so that ended up being a hindrance in like about the first third of this project. And then another big thing that we learned from this was teamwork. We all cooperated very well together, and coordinating everyone was difficult, but it resulted in what we feel is a good product. Okay, so for future development, some refinement is necessary. We have our recommendations back on the slide that Carson covered of maybe adding a relative scale. I've seen ones that are as simple as just bars on a stop that comes out of that tensioning screw, like a couple of bars to show tight, tighter, tightest. And then injection molded plastic for production. And then we just want to thank everybody over at Able. Everybody was a great help to us over there, and a couple of our parts would not have been able to be made without them. Like I mentioned, the gears before, those were machined over there. So they were all a great big help. Professor Ruthier, and then a couple of the other NMU staff, but especially him, he helped a lot with our checking of 3D printed stuff. Anything you guys want to add? Okay, that's it. Any questions? Yes.
I'm curious, did you guys look into the cost of the injection molding process as compared to what you brought the cost down quite a bit for what you guys were working with, but for the cost of building the mold and everything else, and the mold for the several different parts and everything, did you look into what that would be approximately?
We did. We looked into it more in first semester of this project. The cost, it's about $500 for tooling, just tooling setup to set up the injection molding. But then once that injection molding is set up and the tooling is done, it's like pennies per part compared to our $200.
It can cost several $1,000s though for the mold.
Yes, yeah.
These are hundreds
For
of
a proto
dollars.
run, it'd be about $500 and a few $1,000s to set up your, to fully set up a machining process for them.
Thank you.
Yeah. Marley?
So, why did you use, like you're using kind of a hex wrench or an Allen wrench for that final
Yeah.
tightening?
So there's an Allen key in, here you can see we use an Allen key to turn the gears. This is because it was out of our design scope, designing a set set torque wrench. They already make set torque wrenches, so we didn't want to design another torque wrench that already exists on the market. So we just used an Allen key to simplify our project.
When you do go to injection molded parts, your tolerances will be a lot better too. So.
Yes. Yes.
Professor Martin?
The idea for the tension scale, that's an interesting thought. Was that in your original scope and you just never got to it, or was that something you kind of came to see as a benefit along the way, or why wasn't that completed?
It's something we kind of saw on the way. The previous design has a set scale on it, but it's not made by Able currently, and they're relative, so you wouldn't know what the tension was on there. The surgeon would know what tension they like to apply that to. So it's something we didn't have time to implement at the end because it was halfway through our project that we kind of wanted to add that.
And another thing too is that, just like Madison's trying to say, it's really a feel. Like you kind of feel that it's tensioned enough. And that, I watched several videos of other people utilizing different products that are out on the market, and all of the surgeons that use those products say that. I tension it to this, or I tension it to that. It's not like I tension it to specifically this.
So you tension, there's two ways to tension. One you do with the torque wrench, which is what you're using your Allen.
Kind of.
wrench for
The
right
torque
now.
wrench
But
only
then-
rotates the driver, so
Right.
it's locking a collet on the implant itself has an internal collet.
Yep.
So it's not adding any tension, it's just locking it so the tension can't come off.
So
Once
you
you
would torque that torque wrench to a certain torque so your collet is
Yes.
sufficiently gripping it. And then you have your
Mhm.
other nut on the backside.
Yeah.
The wire goes through, that's the tension that you're.
Mhm. There is a set, 30 inch-pounds for that gear is the torque that the driver should accomplish on that implant. That's what it's set for. So you'd want a set torque wrench that could hit 30 inch-pounds when rotated.
Quick question.
Yeah.
When you did your FEA, what material did you use for that?
I used ABS plastic for the jaws, and then stainless steel for the implant.
So, did you say that plastic injection molding would be better? Did you ever do FEA using plastic injection molding or any kind of
What-
plastic that would be used in plastic injection molding?
What we have available on the SolidWorks simulation, I wasn't exactly sure what Able would potentially use in the future, and then on top of that, I felt that there wasn't one specific material in that selection that you get that adequately met those standards.
So, why were you thinking that plastic injection would be strong enough where the rest
So
would?
plastic companies have an ability to pick from multiple different recipes that already exist that have higher strength and
So you
proof off.
did look up?
I did look it up, yes.
That's all I wanted.
Okay.
That's it.
Yep.
Sorry to go back to this again, but why wouldn't a surgeon just use a torque wrench on the back nut as well, not just to lock the collar, but to provide tension. Because you'd be able to equate torque to your back nut to the tension in the cable as well.
That is something we thought of. It's not part of, we didn't decide to go down that design route when we started, but it would be an option moving forward. We're hoping that a class next semester would also take this project on forward and maybe make some changes.
Okay, that's all we got time for. Thank you very much. Chose not to use the lights.
Hey, at least out. Thanks.
Who's next?
Hey, Greg? Are you happy with that? You got a break.
All right, we're on your time, Jensen.
All right.
I'm Nathan Herbst,
And I'm Jeff Byer.
and our project is a portable backcountry tow rope.
You gotta plug in the, it's in this.
What's it in this?
You see? There you go. That didn't happen?
It didn't happen.
That's all right.
And
Okay.
So the project scope is basically me and Jeff are both avid skiers and snowboarders. We both kind of wanted to do something relative to that. It's one of our major hobbies, especially with how long the winter is here in Marquette. We thought it would fit perfectly. Jeff had previously built something very similar to this in high school, obviously not to the degree, so we thought, let's give it another try with more engineering and, more design kind of implemented into it. Being able to set this thing up on any sort of terrain or any sort of open spot that you could ski, obviously drive past something you think, oh, maybe I could set something up and that'd be awesome just to turn into my own personal ski hill for the day, so we thought this would be a really cool idea to do that. So kind of our design overview, it's powered by a pulley system consisting of two separate units. This one right here, this is our main unit, and then we have on the bottom, if you can see it, is our return unit. Obviously creates that entire loop. It has two pulleys on top with the drive pulley down underneath. It's powered by a 6.5 horsepower gas engine. It has 500 feet of rope with obviously looping. You have 250 feet of usable rope, and then obviously the entire frame is aluminum. Its small, kind of compact footprint is obviously entirely for usability and easy portability, as it would be ideally to be put in a sled and towed behind a snowmobile. Setup time takes about 15 to 30 minutes, depending on where you are. Sometimes if you're farther away from a tree, here on the base unit, it takes a little bit longer to get it cinched down and ready to go. But the teardown time is probably about half that, 10, 15 minutes. Our goal was to have this be 125 pounds or less. We came in right at 121 pounds, so we just came in under our goal. And our budget was about $500. So as far as where we're at with the project, this is our finished product. Well, unfortunately, we fell behind schedule. It just came down to some conflicts, scheduling errors here and there. We had great communication, which helped us kind of overcome those conflicts. We only finished about a week late on the build, and we were still able to get 2 testing sessions in, which was our goal when we started this. Each of those sessions lasted about 60 to 90 minutes. Each person would use it about 3 or 4 times going up the hill, and then we actually used it going down the hill to simulate if you wanted to set up something on flat ground, pull yourself, and obviously it gives you artificial speed that you wouldn't have just going flat on a snowboard.
So here's our design process. We first started with a bunch of sketches, just to kind of to see how our ideas kind of work together. We had a setup just to make the math or to calculate and if this motor would have enough power to pull or do what we're doing now. So yeah, we just started with some sketches just to see kind of how we're gonna go about it. So here is our SolidWorks models. Basically, we just designed a frame around an engine model that we already found on the internet because we didn't buy any of the parts yet, so we didn't really have any idea of how big exactly it was. So we found a model that already existed online, and then we designed a frame around it. So as you can see, there's the drive pulley or drive unit at the bottom, and then you have the return unit at the top. So we set it up this way because the drive unit is significantly heavier, so it would make sense to not have to haul it up the rope or up the hill that you're trying to go up. We did make some changes to the return unit. As you can see in this picture, it's a little different than what we ended up doing, but I'll get into that a little later. So during the fabrication, we used a lot of processes to make the device. It's constructed from aluminum tubing, all welded together. We had a lot of help from Kale, and we had some help from some welding students, and we even got to try some welding on our own, so got to learn a lot through that. All the pulley brackets were manufactured on just a manual mill. We were originally intending on using the CNC mills, but we figured it would be a lot easier and quicker just to simplify the design, and it's been a while since we've done CNC stuff, so it was a little easier for us. All the bushings and some spacers were all done on the lathe. We use small steel ATV wheels as our pulleys, and then our drive pulley is actually a mini bike wheel. The engine uses a CVT, so it can adapt to the torque needs as necessary. So it constantly changes its gear ratio. We added some rubber around the drive wheel just to increase grip, and we have a hand-operated throttle and kill switch to safely operate the device from somewhat of a distance and allow you to kill the engine if you need to. We originally designed on having a brake. It is still on the device, but we found that as soon as you kill the engine, the device stops, so the brake would only really be necessary if the engine throttle got stuck, so it might be something we do in the future, but our original design for it wasn't working out, so we decided to omit it. So here's some pictures of the fabrication process. Here's just some welds and some of the setups that we have prior to welding. Here is the final device, and obviously you can see it right here in the corner as well, but this is right immediately after we got it done. So we have some videos now. So this is our first test run. We just set it up in the parking lot just to see if we can even turn the rope in a circle. And so that was the first test run, and obviously it worked pretty well. That was before we added any rubber to the wheel. We were kind of just seeing if the original design would be enough. So here is the setup. So as you can see on the top, this is how the top pulley is set up. You just basically put some ratchet straps around a tree, and it hugs the tree, kind of like a tree stand. And yeah, we put a towel just to protect the tree as well, because we were on NMU property and we didn't want to get in trouble. We have a video of the bottom, the drive pulley setup. We have a couple ratchet straps linked together that we could ratchet in and just increase the tension of our rope. So the ratchet straps worked how we hoped they would, but I think going forward it would have been nice to have a dedicated tensioning system or a longer ratchet strap so you could accommodate different tree lengths. So here is a video of our first real-world test. This was before we added any grip to our drive pulley, and we just kind of wanted to see if the steel would have enough grip. So it did have enough grip to tow us on flat ground, but as soon as I got to the hill, it basically just was slipping on the pulley and didn't really work. So we decided we needed to add some grip to the drive pulley, and we did that in this test. So here's the next day. As you can see, everything melted, but it did have enough power to pull me across grass, so I think we were pretty confident that it would have enough power to pull us up a significant slope. I'll let this go.
That's crazy.
Yeah. And we did find out while testing is that we can pretty easily use it going the other direction. So if we wanted to set up in a field, we could have jumps on either side, and you could have people going in all directions, so it actually worked out pretty well. Just skip to the end, you can see it coming in the other direction. So we ended up getting pretty good speed from that too. And you can't really see it in the video because it's kind of blurry, but we originally had how we connected the two ends of the rope was just a bunch of zip ties, and it worked pretty well the first test, and then we cut them all off and then packed it up, and then our second test, they broke, so it didn't work but we found out we could tie them together, and the pulleys were large enough to allow knots to go through, so it didn't really matter, and the knots are a lot stronger than some zip ties, so. So after their test, we added a final piece to it, and there was a hand throttle, and here's just a video of this operating. So it's just an ATV throttle hooked up to the throttle on the engine, and then we have just a motorcycle kill switch also hooked up, so in case you need to, you can easily kill the engine. Okay, so why this product is better than other things that exist. So it allows lift access to places that you don't have lift access to. You can go out into the woods and set up a ski hill basically. It's more portable than setting up a permanent ski lift because it's obviously temporary, and it's a little easier than snowmobiles to set up, and a lot more cost effective. So you also can use it in either direction, and you have a hand control, and it's fairly cheap compared to anything else that exists on the market. So yeah, why don't you take over from the rest of it?
So we learned a few major lessons during this, and one of them was obviously time management is probably the most important part to your build process. Communication's another one that is very important, but time management is really, we found that was really what makes or breaks the whole build process, and whether you get it done and you have enough time to test before you get hit with a 75-degree week and all your snow evaporates in front of you. We thought 250 feet would be short. As you can see by the video, it ended up being actually a pretty significant distance just for setting something up. So, obviously it can be adapted to where you can swap in smaller ropes, but we thought 250 feet might be too long, or it might be too short, and ended up being maybe even a little too long. The total footprint of the design could be a little bit smaller. We have two support bars on the actual side that you can't see on the back side here. Those can be reduced maybe down to one larger bar, and obviously have reduced the footprint of the entire device just a little bit. The device could benefit from a better tensioning system. If you can see there's a tensioner already on our drive chain right here. It was a little loose when we had put it on, so we made that. It could even be improved even further. Some conclusions is our product works obviously as intended, as you saw by the videos. It can pull someone pretty fast up a slope. It was within range of what we wanted to be for our weight and with our cost. This was a really good experience, at least for designing something from the ground up with, just with an idea and building it as well. Some future plans for our design is obviously the braking system could be revamped and finished. Obviously, we ended up admitting it from this project just as we didn't have enough time to really finish it and kind of implement it the way we wanted it to. The length of rope, like I said, could be modified. As obviously these pulleys come out pretty easily. They're just in with cotter pins. The rope got kind of hot, especially someone grabbing it, and it would create a little bit of tension doing that, and even holding onto it, the rope would create a little friction, especially on that drive pulley. So a way of cooling that rope is something that could definitely be added and make sure it doesn't fray or even hurt the drive pulley and its traction. Covering up the device to reduce sound and to reduce noise. It'd be pretty easy, wouldn't take a whole lot to cover up the engine a little bit and reduce the noises you get heard by the videos. It's pretty loud, and in person, it's pretty loud. We got a lot of stares. We were just out there, people driving by wondering what we're doing. And we'd like to thank everybody in the MET program, especially Kale and Seth, for helping us out. I know Kale helped us weld a few things, and Seth was able to get the shop open on the weekends for us, so we could further the design and get this finished up in time.
And the cost of this would have been a lot greater if we didn't have access to some of the materials, but everything else, yeah, done pretty well. So, any questions?
I actually only have a comment that I didn't notice before. This isn't a gotcha thing. I just noticed that your tensioner is on the drive side of the chain.
No, the drive side actually is on the bottom. Yeah, it drives.
Is it?
Yeah. We had to do it that way because normally these engines are set up to run on the other side, but just how the pulleys worked out, we had it like that.
Oh, I got what you're saying. So you're saying the torque converter is usually on the other side?
Yeah, it's usually on the other side.
Gotcha,
but
okay.
you're not gonna
That makes sense.
Yeah. So that's why we see it off.
Yeah.
But, yeah. Yes.
Is there a reason why you used fairly small rope? I think on snowboard hills, they have really thick ropes that are easy to grab.
So, yeah, we were basically looking for the thickest rope we could without it weighing a ridiculous amount. If you go up the next size, it weighs about 60 pounds, 70 pounds heavier, and it's just there's no real benefit. This is plenty thick to grab onto, especially since it's not continually running. You go up and grab it, and then you rev up the engine, and then it goes. So you already have the grip in your hand, and yeah, anything larger would have just been more expensive and more heavy and wouldn't have had any benefits. So, yeah.
So I was out on the mountain with a few of my buddies. Could I have multiple people on the rope at the same time, or would we have to turn the motor on and off each time one person wanted to go out?
We did test friction on it, so we added a skateboard that had off-road wheels, and we said, all right, can it pull this? And that's the one time we had it burst and come off. So we figured that about two people weighing 150, 170 pounds going in either direction would probably be its limit.
Okay.
We don't think anything more than that would probably just bust or so some pulley would fail.
Our original design was just to have one person and have it be a single use, but I believe this engine is plenty strong to tow more people. It's designed to tow one person up a 45-degree incline. So if you can find a 45-degree incline around here, then but everything else will be 20 degrees, and you could easily tow more than one person. Yes.
So with those design parameters in mind, 45 degrees, 200-pound person, some friction, did you come up with a horsepower that you need at the outset?
I don't know if we came up with when we did the calculations, we calculated based off this engine that existed already because it was just an easy, cheap engine to use. And we did find that 6.5 was enough. I don't recall the exact horsepower that was required, but
I think the perfect horsepower was around 7.5 horsepower is what we found.
Yeah, and I think, but that was also for a certain speed that we were aiming at.
The total force that you have to push times the speed feet. And
Yeah.
Or that horsepower, right?
And we did end up changing our gear ratios, especially with the CVT. It's a little different because it's a variable gear ratio. So we ended up, our calculations that we previously did were for a faster gear ratio. So we knew that the CVT would work better and have more torque. So yeah.
No more questions. All right, well done. Start when you're ready.
That button moves forward, and then there's a little bit of I'm Elijah Muxlow. I'm Benjamin Muxlow.
I'm Joseph Otavero, and this is our pipe friction demonstrator. As you can see, this is what our actual design looks like with some of the major items labeled. This is what we're going to cover. We're going to cover our motivations, design, highlights, and project overview, our status, risks and assessments, applied principles, fabrication and assembly, key results, and how we would market this in the real world, and then we'll have our conclusion. So the background and motivation for this project is in Senior Design 1, Professor Norberg asked if anyone would be interested in doing something for the fluid mechanics program here at NMU, and we couldn't think of anything, so we took him up on that offer. This is also going to be extremely beneficial to any of the students who are taking fluid mechanics here, as it will help demonstrate fluids in a real world situation instead of just what you would learn on paper. So for some of our design highlights, we went with semi-mechanical gauges. They have a digital display, but they're a mechanical gauge. They have readings in bar, PSI, and MPa, and they're placed in key locations around the system. And they are going to be used to calculate and show losses throughout the system. For valves, we used gate valves and ball valves to deviate flow throughout the system, and we use globe valves, ball valves, and check valves to provide losses throughout our system. For our pump, we used a half horsepower 3-phase pump with a variable speed drive that converted from 120 to 243 phase. And for our flow meter, it measures GPM total, so it has to be reset and measured by hand as the system runs.
So currently, our project is complete from what we initially proposed. We got our major loss line and our minor loss line on there. We just finished up our reservoir that catches for our major loss line, and it works beautifully, and we get values that we like. We are looking into replacement fluids because currently it is loaded with water, which we don't get the PSI that we want. We ran it with Rycon hydraulic fluid before. Also not ideal, it was a little too thick. So we're currently researching a non-corrosive, low viscosity fluid to run through the system. We submitted an IMECE, which is International Mechanical Engineering Congress and Exposition abstract in early March. We're still waiting to hear back on the results from that, but we're pretty hopeful that they'll accept it, and once that's accepted, we will be asked to create a poster, and then we'll get the opportunity to go down to New Orleans and present our project to the IMECE this was kind of our schedule that we ran along with for the most part. We got behind by about 3 weeks, 4 weeks on our frame due to snow day. So we originally we were going to meet up on Thursdays. We had 2 Thursday snow days in a row. That set us back. And once we did finally get the welding going and we got our frame kind of assembled and going together, then we flew through the rest of it pretty fast. So we've had our project together now for a good week now, and our values are looking good. Once we get that new hydraulic fluid in, we're hopeful that it's going to be the end that we wanted. So these are some analysis that we did on the frame. We originally, in our original model, had 2" by 1" aluminum frame for pretty much the entire thing, and we ended up using some stock that Cale had in his shop, and it's about 1" by 1 1/4" roughly, so sized down quite a bit. And we had to do some analysis to figure out, we got a pretty heavy load sitting on that plate there. I think the hydraulic tank is 50 pounds, and then loaded with fluid, we're sitting at about a 100-pound load. Yep. Yeah, the analysis here is a 120-pound load. As you can see, we only get about 3 millimeters displacement on the center there, and even less on the frame. And after completion, we have maybe 1 millimeter or 2 displacement. So frame holds up really good to heavy loads. We're definitely satisfied with that. So we've had some risk, and we followed some standards with this. Our casters, they are our base of our frame. They each hold up about 100 pounds to 150 pounds. So we got 4 casters, and it's very sturdy. It has no issue supporting the weight. We even when we climb up onto it to look down into the reservoirs, it's got no issues holding us up. We had a variable speed drive. We had some issues with that where it was grounding to our frame, and a couple of us got shocked pretty good. So we had to find a plastic enclosure to put that into, and now it's safe and it's no longer grounding to our frame. So that's been nice to have implemented. We use the general energy equation and the Reynolds number to kind of use on analysis for our systems. That's how we find our minor losses and major losses.
Both of them were able to tell me that 120 volts hurts pretty bad. So for our applications of proper engineering, I made a spreadsheet for our top line that had various equations for flow rate, Reynolds number, head loss. So here we have our Reynolds number. This is going to determine if we have laminar flow, which is a smooth, clean flow, or a turbulent flow, which is bubbly and disturbed. So for water, we have currently on this spreadsheet a GPM of 5 gallons per minute. We have a Reynolds number of, I believe, 20,000 at 5 GPMs, which is a high Reynolds number for fairly low flow rate. Our variable speed drive allows us to go down to a much lower flow rate and achieve laminar, which we'll show in a second. The viscosities we used on this line right here were found on tables online. Water has a viscosity of 0.501, which is 1 centipoise. So we were looking for a hydraulic fluid that was somewhere in between the Ricon that we used and the water that we are currently using. And Cale offered a fix with this weld fluid here. I couldn't find the viscosity for that fluid, but I looked up online that it is a 50%, 50-50 mixture of deionized water and ethylene glycol, which gives us a viscosity of about 0.00005, which is about 5 centipoise. And then at 5 GPMs, we're right in the transition zone at 3,900 Reynolds number, which is about 10 underneath turbulent flow. So then, so we have also a couple calculations here for friction, which determines the friction that we have going through the pipe, higher Reynolds numbers equal stronger frictions. So with a Reynolds number of under 2,000, which is laminar flow, we can use the formula 64 over Reynolds number. That'll give us our frictions. For the most part, they're very small, not a lot of friction. And then when we up Reynolds number, we use the chart on the next page called the Moody diagram, where on our X we have Reynolds number, and then on our Y on the right side we have pipe roughness. We use those two values along with this section of the Moody diagram to determine our friction factor in the turbulent range. So here's a little demonstration of our top line, sorry that is blurry, shooting out laminar flow at a GPM of about 2 gallons per minute. And we do have one design fix that we can do in the future where we're going to increase the size of the plexiglass tank, because when it's running turbulent, you can no longer see inside the plexiglass. So here are two of our pressure gauges. These are the pressure gauges on the bottom line, which we are using to find minor and major losses. So our first pressure gauge, we get a reading at 13.7 psi, and this is when our variable speed drive is maxed out at 60 hertz. And when the water runs through the line, we get a PSI reading of 0.2 on our last line, so the losses are quite significant. Changing the fluid to something with higher viscosity would give us better pressure readings, higher pressure readings for both, and I have not yet been able to find the calculations to see if this is 100% correct, but in theory it works. So now I have to find the values for the minor losses of the valves and the 90-degree bends. Once I find those, I'll be able to determine if these numbers are correct and usable for a lab in the fluids mechanics course. So fabrication and assembly highlights. We used an aluminum frame for lightweight mobility, mounted on the casters. When that frame, so it's lightweight, the whole project will weigh around 200 pounds, around 200 pounds, and we've been testing it now. It's very mobile. It takes almost no effort to push the project around the shop room. And then we used aluminum given to us by Professor Polkinghorn to keep costs down on our project, along with also salvaging the pump and the variable speed drive from the previous pipe friction demonstrator that was here at Northern, and that kept our budget down by about $1,500 between the two items. So we selected black pipe because the system, we wanted high friction, and it's got a high coefficient of friction, and we get a lot of losses when we're running black pipe, when we're running their fluid through the black pipe. And then we have no prototypes of the project. We just kind of edited the project as we went along. One of our key changes that we had when we built the project was we changed the return line, which is after all of our pressure readings, the line that feeds fluid back into our holding tank. We changed it from 3/4 inch to 1 inch because the tank up on the major loss line was not dumping fast enough, and we were getting backflow, too much backflow. So we we increased the size, and it worked very well in increasing the drain speed. Another change we made was we added a ball valve onto the return line so that when we were running fluid through our bottom line, our major and minor loss line, the fluid would not take the path of least resistance, which was up into our other reservoir, which we experienced. And adding that valve allowed for the system to be closed, and the fluid is forced into the holding tank. So key results, when we were running our variable speed drive, here can be seen at 35.6 hertz, we got a reading on our first gauge of 1.2 psi, on the second gauge 0.6 psi. This was for our top line. The math for the top line is when you have, say, a 9-foot section, you have one pressure gauge at the beginning, one in the middle, and then if you leave it open to atmosphere at the end, you will have 0 gauge pressure atmospheric, and then at the front end you'll have your 1 pressure reading, and then halfway through you'll be getting exactly half, and we achieved that on our major loss line. This is mine. Business case and applicability. The design we chose was better for a lab for the fluids mechanics class. It allows more students to stand around the project as it's running. They will be able to see the flow coming out of the exit of the top into the plexiglass in the video that I demonstrated. The project is mobile. It moves easy through most doors as long as they're 38 plus inches wide. The project stayed well within our budget. We had a budget of $5,000 from Northern, and we were just at $4,000 on the project budget. And then we are currently looking into a non-corrosive fluid, which is the weld fluid that Professor Polkinghorn's provided us with, to ensure that the project lasts much longer. In conclusion, we learned valuable project and time management skills that will help us in our careers. We set up Microsoft project schedules to kind of monitor with. We communicated with each other to make sure we were where we needed to be. We did a lot of troubleshooting on this project. Took us a while to get the welding going, but we got some good welding experience in. We also had help from Dr. Polkinghorn with welding our frame up. The pump and speed drive, they work well. They were a huge bonus for our project, being able to control our flow rate. Our top line achieves laminar and turbulent flow, which is what we desired. We just need to make some few design changes to increase the size of our catching reservoir so that we can see it without it feeding back on itself. Future improvements are a big part of what we wanted in this project. We left room for more lines to be added throughout our side that we're currently on, and there's also room on the other side of the frame where in the future we could add on another reservoir or perhaps just more lines even. So far we've used hydraulic fluid and water. Our demonstrator can use pretty much most fluids, water, oil, coolant. Water we do want to go away from because it is causing some corrosion in our black pipe already, so we're going to switch to non-corrosive fluid to kind of get away from that. I'd like to thank NMU for sponsoring this project, and I'd like to thank Dr. Norberg and Dr. Polkinghorn for all the help we've gotten. Also, we've had a lot of help from multiple electrical engineering technology students that helped us wire up our drive and address our issues with our grounding. Thank you for your time. Any thoughts or questions? Yep.
I'm curious, have you thought about putting a little data acquisition in there? Maybe hooking up some of the sensors right in LabVIEW, that way you could compare and contrast like different fluids and thing, or different rates and everything. You could save some of the data and compare it later.
We thought about that, and it's definitely something we would look into because the flow meter currently is not the greatest flow meter, and changing it over to a LabVIEW sensor would give us a much more accurate flow measurement. And also the pressure gauges. Pressure gauges could be changed eventually, but they work pretty well. The main one is the flow meter, and then also maybe a temperature sensor so that we could determine the viscosity, because viscosity is very much related to temperature.
What's the main motivation for changing the fluid? Was it the pressure issues you were having, or I wasn't quite clear exactly why you
Yeah, so
wanted to change the fluid?
we were expecting a pretty large flow rate with this project, upwards of roughly 30 to 40 gallons per minute. And while running Rycon hydraulic fluid, we were maxing out around 7.1 gallons per minute. And so we just wanted our results to be closer to what we
originally calculated. So we switched it to water, which does boost our gallons per minute very high. Yeah, it maxes it to right around 30 gallons per minute. The pump the pump that we had was not made to run the higher viscosity hydraulic fluid that we had, because it was about 30
It was 25 centipoise and our pump's rated for 20.
Yeah.
So the water works good, but you want to switch because of the corrosion.
The corrosion, yeah.
Gotcha.
Somewhere right in the middle between the two would be perfect. Any more questions?
All right. Well done.
So if you want to use the sliding doors, plug this in, this is the, here's your phone number. You want to use the sliding doors?
It's too late now. Wish I could see that screen. Guys, questions ready?
Whenever you're ready.
All right, so our project, we had the power sports lift. I'm Sawyer, this is Anthony and Daniel. Some of the things we're going to go over today, the project overview, the design process and fabrication, the project status within that, project management, and some of our test results. Our design highlights, we had a few of those, results, application, and then our summary.
All right, so project overview. We sat down back in September, brainstormed a whole bunch of different ideas for projects, issues that we might want to tackle, things that we'd find interesting. And we finally settled on a power sports lift. All three of us own motorcycles and have years of experience loading and unloading using ramps and the issues that come with that. So our original problem statement was to design a safe, user-friendly, and effective tool to aid in loading and unloading various power sport equipment and hopefully avoid situations like this one.
So in the first semester, we brainstormed quite a few ideas, did a few rough sketches, and on the left-hand side, you'll see the original winch design we came up with. The right-hand side shows like a gear, sprocket, and chain design. We also had brought up hydraulic system, and with cost and everything, the winch drive and me already having the winch, it was definitely the way to go.
So once we finished up our sketches, we turned to SolidWorks to complete our model. Here you can see our full SolidWorks model with all of our components and 4 sub-assemblies. Like Daniel mentioned, our main goal was safety, so we tried to reflect that in the SolidWorks model. And we didn't have a proper model of our winch, so that's just something we found online just to represent the space it would take up. Here you can see a kind of closer view of our sub-assemblies. Our 100 is the base assembly that all of the components attached to and the carriage rolls on. 200 is our slide-out assembly that supports the carriage while it's loading and unloading and guides the cable in that action as well. 300 is the carriage itself, which is what the vehicles get strapped to and what moves in and out of the truck bed. 400 is the T-handle, which accounts for some adjustment that goes in the top of the slide-out, or the hold-down tube you can see on the top left. And that counts for the adjustment holding the base into the truck bed.
All right, so as far as fabrication, we just started with a whole pile of raw metal. It was a bit of an adventure finding where that was delivered. And then it was just a whole series of cut to length and then weld and grind for the assembly of the different sub-assemblies. So you can see the 200 assembly and the 100 assembly sitting there on the floor. We did have some machined components. We'll talk about those a little bit later in the slides. And then we had a chance to use the CNC plasma table, which was a neat experience, really helpful tool for making all those tabs you can see on the bottom left. Those ended up being the different hinge points for the hold down arms and then holders for the rollers as well. So like I said, we just have basic structural steels, outdoor rated plywood, stainless steel stock for the machine components, so the different rollers. We use brass bushings inside of polyurethane rollers on the carriage, so you'll see those in a little bit, as well as stainless hardware, the winch and paint. The only components that we purchased specifically for this project were the structural steels and then the paint and plywood and hardware. So that cost came to around $670. Like we said, Sawyer already had the winch, I had some of the rollers and stuff, so if we factored all of that in, we'd be close to around the $1,000 mark. And then every week's meeting was Main Street Pizza, so that added some costs as well.
Here's our Microsoft project outline. We followed this pretty closely. We mixed up the order of a few things just based on what was a little more intuitive than what we planned out. But we hit pretty much every major deadline and stayed on track to this pretty well. We have a few more testing iterations to do, as you'll see in the next slide. But we should finish those up this week. And we also deferred the user and installation manuals to finish all of our alterations. We did a little bit more than we were expecting, and that took a bit more time. But the manuals aren't due until the 28th. Here's our project results. You can see we still have a few tests left to do, but we had a main criteria that we used to judge each of these tests. It was based on a point system. 1 point was for safety. Just basically if the user gets within 1 foot of any pinch points, that would be between the carriage and the rollers. Effectivity was any assist that you needed to do if the rollers weren't quite in the right track. And just 1 point for general effort required, how much effort it did take to move things around. So you can see there on the right-hand side we have all of our test results. We're pretty happy with what we're trying to achieve. We're going under 4 points per cycle, which is an unload and load. We got to that goal for most of them, except for the 2 bikes. Definitely our greatest challenge. Here's where the project currently lies. Everything is fully painted and assembled. You can see on the left-hand side would be the initial stage where you load your bikes, and the 2 following pictures are the carriage being lifted into the truck bed. Like I mentioned before, we just have a few tests left to do, but all of the build is completed.
Alright, our design highlights. The final product very closely resembled the models that we drew up first semester. Our T-handle creation was probably the best part of this project. We went into this not really knowing how this would work, and it utilizes a 1/4 inch of adjustment each time. And so we have the external tube, the inner tube, and the T-handle that's shown in red in the right picture. That slides into the inner tube, and then the inner tube slides into the external tube. And the holes are misaligned by a 1/4 inch, so you get that 1/4 inch adjustment all the way from 16 to 25 inches, depending on how tall your truck bed is. And it worked out phenomenal. As long as you tighten it up for with the tubes and put the pin in, it doesn't take much force to put that T-handle underneath the truck bed for it to be secure.
So our original goal was a single bolt, which would go toward the front of the truck bed. Obviously that's not ideal because you'd have to drill a truck bed to install our product. And our heaviest test so far was almost 600 pounds, and we don't have a single bolt. So we're just using those hold downs, and we haven't had it move whatsoever. So.
Another design highlight we had was, we call it the big switch. All the professors kind of helped us out with this. We didn't really want to do it at first because we didn't know if we had enough time to complete this, and one day we just pulled the trigger and did it. We needed it for more stability and strength, because using that single cable, if the bike was loaded uneven, I mean, one side would get pulled up faster than the other. And so it consisted of making 2 machine rollers of stainless steel that are on the bottom carriage that are welded up in front with 2 brackets, and then that feeds the wire into the winch, and the winch goes right into the top carriage here and hooks underneath. So it definitely gave us a lot more strength and stability.
So to compare our result to our original design specs, those pictures on the right were the single cable setup. Like Sawyer said, it was recommended very early on. I want to say October, November, that we go with 2 cables. We thought we knew better, but it turns out Kale's idea was superior. One test in, we swapped to that dual cable system for the stability and strength and deleted that center roller that you can see in the top right picture. Our original goal was a footprint of 72 by 48 inches, so kind of fit in any truck, including short beds. We're just over our length goal, so we're around 76 inches currently, but you're still able to close the tailgate on a short bed truck, a 6.5 foot bed. Our max weight of our assembly all put together, our goal was 125 pounds. We're right around the 150, 160 mark, but with that increased weight of our assembly, we actually gained some weight capacity with the rigidity that was added. So our goal was 500 pounds. Like I said, our heaviest test so far was close to 600 pounds, and we think that we could go upwards of 800 to 900 pounds. Time for use and installation time are both pretty accurate with our original goals. For as many times as we've had this in and out of the truck, I'd say we can install it in under 5 or 6 minutes.
So we did a few tests, like Anthony said, we have a couple tests left to do, but the best case scenario is testing the product with no load. This video is showing just that. As you can see, it's getting pulled up evenly with the dual cables, and then we were thinking we were going to have a problem of it slamming down into the bed of the truck, but even with the load on it, it doesn't slam down. So normal use, we're gonna try and plan for 2 dirt bikes, but that's kind of worst case scenario. It is really tight. We had 48 inches, right? 48 inches for the width, and for the short bed truck, and this equals out to 244 pounds for the single load of the dirt bike, and that video showing just that. It uses a little bit of effort, so we had to mark a point for this test. But all you have to do is press on that back corner, put it right back on track, and it loads perfectly fine.
So some applications. Regarding our original problem statement, we far exceeded our goals. We ended up with a very safe, very user-friendly, very effective product. Accomplished everything we wanted it to with none of the risks associated with ramps like you saw in that first video. We ended up with a very durable product, so corrosion resistant, every surface is painted. We did use a wooden deck, as you can see on the carriage, but that's fully sealed as well, so we have no risk of rust or corrosion failures. Our cost was much lower than products that achieve much less than ours. So a really nice set of trifold aluminum ramps can be upwards of $1,000. Something like a bed slide where it pulls out of the bed of the truck but doesn't lay flat to the ground can be upwards of $2,000. And like I said, if you had to purchase all of these components, we're at roughly $1,000. In summary, some lessons we learned: teamwork and time management are both really key. CAD to prototype, or what works in real life going back into CAD, is not so simple. So we use SolidWorks for most of our modeling. Things that look great in SolidWorks don't always work in real life. And maybe you can build something that didn't look great in SolidWorks but works great in real life. And sometimes our professors and experienced engineers know a thing or two. We did create, as part of our assignment, we did have some points assigned to creating social media regarding our product. So we do have an Instagram page and a very loyal 45 followers. So we will still be posting some different test results in the finished product as we wrap that up. So thank you guys for your time. Thanks to the engineering staff as well for all of their help and recommendations. So are there any questions? Go ahead.
You guys mentioned that you were selling this thing. How much would you sell it for?
So that is a good question.
I just wondered.
No, the winch was Sawyer's, and his goal is to keep that, and it's a much heavier winch than is actually required. So we have a 3,500 pound winch on it currently. Something in the range of like a 750 to 1,000 pound winch would be more than sufficient, which would be quite a bit cheaper. So if we were to sell just the framework with the carriage and stuff, I'd say like $800 would still pay us for some of our time, and then someone could purchase a winch for $150 or so.
We could definitely mark it up even more than that if we wanted to.
Yeah,
I mean, if we marked it up to $1,800, it's going to be cheaper than all the other products out there. Oh.
Okay, so this was Sawyer's brilliant idea, actually. It's our first initials, it's Daniel, Anthony, and Sawyer, but it means the in German, so the
Not
truck
that
bed
German.
lift. That's the extent of the German that Sawyer knew. So.
Yeah.
Can you also use different vehicles other than motorbikes on this?
Yes, yeah. If you had a relatively narrow quad, like a race quad or a smaller utility quad that fit between the wheel wells of a truck, you could easily load that on here and use that. A snowmobile would tend to be longer than our assembly. As long as you didn't mind the track dragging slightly, you could load a snowmobile with it. And then the possibilities are really endless. Anything that is heavy and needs to be loaded, someone with like a welding rig but still wants to use their truck bed on weekends could leave all their welding equipment on it, offload it in their garage and unhook it. Something like an overland camping setup, ice fishing stuff, hunting, really any application. So.
You guys came on a track at one point, and I saw you reach over and touch it, get it back in.
Yeah.
Any ideas, brainstorm between the three of you to keep it in line without any shifting?
We did, yeah. I don't know if you've ever seen so we use V-rollers on the back, that slide out portion, and there's angle iron on the bottom of the carriage that rides in those V-rollers. So if you've ever seen like a boat trailer where there's a series of rollers that are all connected in a row,
Yeah.
if we had just 4 V-rollers on the back instead of 2 that could pivot, it would keep it straight in that tipping point where it's not touching the ground or the truck bed.
We were also talking with Kale, maybe a simple grab handle. So when it's
Right.
in the air, just grab that grab handle, kind of wiggle it back and track, and
I think if you find that exact spot where it comes down, because I think it comes down pretty consistent, I was actually thinking on the inside you could put some little deflector
So it kicks it
shield,
over.
so it always funnels back
Funnels it
down
into the track.
Yeah.
So that way it would just slide down the funnel, because you probably have that much space underneath there that you can do that.
yeah.
Mm. Any other questions?
Good job, gentlemen.
All right, nice job.
Thank you.
Our next group is going to connect over Zoom. They're down in Wisconsin, so bear with me while I set this up.
Oh, well, I-
Where's the little knife?
Just our prefix cards.
Exertion.
Could this up the game? Oh, yeah. Maybe I do.
Give us an audio check.
It's like 20% red sausage.
Do another one, please. Is that okay? Yeah, okay. How about Christian? Can you give us an audio check?
Check, can you hear me?
Yeah, both are good. All right, so I have the podium viewpoint for you, so that's the audience you got. And I'll be around to help when we get to Q&A. All right. With that, take it away.
Brianna?
We got you now.
Okay.
coming out once again to talk about what's our presentation on the project we're doing. Is an automatic lens wood cutting machine. So essentially, the objective of this project was to create a accurate cut the length machine to cut wood, to use a cutlass to set up all the cut lengths and then proceed by making all those cuts. The plan was to have this done double the standard rate and a manual cutting process with a budget of about $400. The design features a 9-foot hollow channel with a slide mount servo friction roller. The plan was to have an HMI position entry where you enter your cutlass. Designed economically with low cost and donated parts. Recommending for hobbyists. At this point, we consider the project complete. So build specification is automatic lane guide system with an interface. The budget within $400. Accurate cuts within an eighth of an inch. Safe and reliable. All the specifications were met. Stepper friction roller, laptop interface. We were under the budget, and the accuracy was on point to where we wanted to be, and it was very safe and reliable and repeatable. We had some design changes. The old design, we wanted to use a HMI interface, but the time frame wouldn't allow us to do that. We wanted to go with a PLC controller and safety logic relays. We had to change the design a little bit. We had some problems with connecting to the PLC and the HMI. We were not able to get it to talk to the PLC at all. So the new design, we went with a laptop interface, Visual Studio software. We went with the Arduino controller instead of the PLC, and safety disconnects, or disconnect safety. So essentially, this is it from the test plan we wanted to do, and as you can see, the numbers are within the specification that we wanted it to be. Pretty much we were right on, with between a 16/32 and eighth of an inch in every test that we have done. So we have completed this project. Everything was completed on schedule, apart from the test plan and the instruction manuals, our manual, which are still in progress, and we should have it by the end of the semester. So some of the standards we wanted to follow. We actually got it done. The OSHA safety standards were met. All electrical is labeled. The safety disconnect is installed. The panel assembly. And the saw garden.
Alright, so this is a picture of the printed interior caster slide on the upper left. We 3D printed our components, which saved us a lot in cost. We actually had these quoted, and it would have been upwards of $1,000 just at the top slide machined. But by 3D printing the parts, we drastically reduced that. The upper right is the top assembly and the bottom assembly fastened together. The bottom left is the top assembly, and then the bottom right is the top assembly being printed. Here you can see the computer interface. The top portion is how we set the COM port and the baud rate for the Arduino connection. Connection is then initiated with the connect button, which is what the disconnect button turns into when you click it. On the right, we have the current position, which tells us where the stop is at any given moment. We also have a move to position button and a manual entry field, so you can enter however many inches you want. Below this, we can increment by single steps or single inches. You can also increment. On the left, we have a cut list that shows the 10 previous entered cuts in a rolling list. These are easily selectable with our list buttons, and when click, the stop button the stop will move to the listed position. We also have the still position button, which allows the roller to move to a section between the studs, so it can be the table can be folded up, and a home position, which brings the stop to the edge of the saw blade. We have a video of the saw and cut to length components. Here we can see the rail mounted system, 2x4 saw stop. Along the back is the button used as a sensor for the home position. The stepper motor on the rail mounted system is what contacts the button. There's the electrical. If we home the setup, it'll move to the button until contact is made. And then it'll slowly back off until its contact is broken. We can send the stop out 16 inches and also bring up the saw for a cut. And then we home it between moves so that there's no step loss occurs for the next position. Next, we have a video of making a cut. Here we can see 16 inches is entered into the laptop interface. The stop moves to 16 inches. We can then place our board against the stop and make the cut. As you can see with the tape, we've made a perfect 16-inch cut. Moving back to the interface, we can see that a cut list option of 16 was used. The list for our design was a very basic prototype with the printed components and the cheap Arduino controller, drive, and stepper motor changes. We feel it was redesigned and it could be fairly competitive in the construction industry. Other competitors offer something similar for upwards of $4,000. Fairly significant cost difference, even after applying labor and component expenses and discounting bulk manufacturing expenses from our design. Over Over the course of assembling the project, we became aware of some design flaws. Our friction rollers prone to skipping or getting stuck on uneven surfaces provided by the old and deformed pallet rack upright we used. This could be addressed by using a 9-foot piece of extruded aluminum and a timing belt, kind of like a linear slide. We also found it's difficult to maintain positions when the open loop stepper motor was pushed off course, which would have been addressed by the closed loop system with an encoder. Finally, our current design was mounted to a table and not very portable. We figured making the system portable would expand the capacity for its usage. By connecting a linear rail made from extruded aluminum onto a portable saw table, we would open up our design to many construction tasks. We could also make an app that could connect to the controller via Bluetooth, which would eliminate our need for an interface and the cost associated with that. To conclude, we learned a great deal over the course of this project to achieve greater understanding of programming Arduinos in C and stepper motor control, acceleration and speed control. We also learned how to design graphic user interfaces with Visual Studio. And with all the coding, we experienced a great deal of troubleshooting. We also learned a lot about project management, including risk assessment, reporting, designing, timelines, and more. Alongside that, we learned how to develop professional project reports and associated data. We learned how to use, maintain, and slice models with 3D printers as well. We'd like to acknowledge FTC for 3D printing and thank them for their PLA that we used. We'd also like to thank GreenHack and Footlocker for the electrical components, and Dr. Seth Norberg and all the electrical engineering faculty for their excellent teaching.
All right, questions?
So I have a question, gentlemen. Can you cut less than 16 inches in length? And have you tried sampling multiple pieces out of one 8-foot board?
So yes, you can make up to, down to 3/4 inch cut, and up to 8 feet. We only tested 10 inches, 16 inches, and 24 and 48. But we feel confident with the amount of variance that we received between all of them that it was pretty spot on.
Did you have a second part of that question?
Yeah, I guess the second part was, when they demonstrated it, you guys put one longer, like a 17-inch piece on and cut it to 16. My question is, if I put an 8-foot board on there, can I get 8 consecutive 10-inch cuts off the one 8-foot board? They'll get home every time, that's what I thought.
We had it designed so you would move it to 10 inches, and the stop would go to 10 inches, and then you would take the board from the right and just cut off 10-inch sections at a time.
Gotcha. Thank you.
Yep.
Other questions? All right, well, I appreciate the video. That was very, very helpful on what you had done. What did you struggle with most as you went through this project?
I would say probably the programming. There was a lot of troubleshooting, checking code syntax, and then while loops getting stuck, and if statements not triggering.
How did you determine like the length of how far you were cutting? I guess how was that determined for electrical? No, like in the coding wise.
were you able to hear that?
Sorry, I didn't hear the question.
Try to project to this thing.
Okay.
Or where,
How are you able to code in a distance? How are you able to determine how far you are moving?
So there's some math behind the code. If you enter 48 inches, we calculated that that would take 21.25 steps of the motor, and we used a float variable to multiply that by the inches that were entered into the GUI, and then we rounded that so that it was an integer, and then the stepper moved to that position.
So what was the interface for the stepper motor driver? Did it have a serial interface? How did you communicate with the stepper motor driver?
Yeah, it was a serial interface to the Arduino, which connected to the stepper motor driver.
So you would just send either forward or reverse and a number of steps, and that's what the stepper motor would do?
Yes. Yep.
All right, any more? Okay, well, nice job. All right, gents, I'll see you next time. Feel free to keep watching on the YouTube channel. All right, who we got next?
Testing.
All right, so we have the penultimate group here. Are you? Yeah.
Oh.
All right.
Oh, I thought this was a source room. Alright, toss. Oh, look at that.
Quite, yeah.
Whatever you
We're a couple minutes early, but
Does that mean I can take all the time I need?
I appreciate. Why don't you put the hat back
Was I blinding you?
There wasn't clear.
If I'm not, you're not.
If I'm not,
All right, well, good night, evening, faculty, friends, and auxiliaries. Thank you for coming to our presentation on the automation control system. If anyone doesn't know, I'm Sam, this is Kenny, and this is Neil. So, carry on. Project overview, we started this by wanting a thing called a smart mower. It's basically a Roomba for your yard that like goes around the perimeter, then fills it in and cuts your grass so you don't have to do anything. Yeah. So now we've built a system that can go onto the mower without the mower. So it's an applicant system that can go on a lot of different things, not just for cutting grass. We have decided to call this prototype system Peter. I'll hand off Peter to Kenny.
So our prototype Peter is short for PID, Engineered Applicable Technological Encoded Robot, and he's just been a blast to be working with. So our status right now in our project, right now we are unfortunately not 100% complete. We are still having troubles with our route running function. We're having troubles going from the first waypoint to the second waypoint. It's kind of going out of line, and we've been trying to troubleshoot that. So
On the other not yet completed aspects, we also have the complex mapping shapes we haven't tested out. The mapping, basically like star shapes and stuff like that. We had a battery indicator idea, and that was not yet completed, as well as the user width input. That the width input is used for the mapping algorithm. On the other hand, the working aspects of Peter, we have the obstacle avoidance system. We have a controller that works. He is able to obtain waypoints and actually show a map of what the area looks like. We have a compass that, once calibrated, works and is accurate to plus or minus 2 degrees. We have a GPS module that will give us accurate coordinates. And we also have encoders that will give us accurate ticks on each Hall effect sensor rotations.
So, for the design highlights, so obstacle avoidance, as Kenny has previously mentioned, is able to detect static as well as dynamic objects, as well as multiple objects in its path. The controller, which consists of the mapping switch, the run route switch, the fill route switch, and the waypoint reset switch. The transceiver, which is confirmed a communication up to 800 meters, open field. And the route running, as well as the closed loop PID.
So just a basic going over our controller. We have this, this is the prototype, Mark 1. It's a box that holds everything. We, in our last presentation, talked about how we had a 2 joystick control. We brought that down to 1 for X and Y axis. We have 4 buttons, that's 4 switches, for controlling our mapping, route running, our reset waypoint, and the fill-in map functions. 2 LEDs that indicate if you're in map ring when you're driving it around to set the original map position, and then green runs the route. So you just flip it over when you're done.
So the design process for Peter, exactly what is inside Peter. We have a multiple fusion of sensors working with one another to complete our route running algorithm and mapping algorithm. We have an ultrasonic sensor for the obstacle avoidance, and it measures distance between an object in front of him and between the distance between Peter and the object in front of him. We have the GPS module that gives us the coordinates. We have a 3-axis compass that is used for when Peter is turning. We use angles of degrees to turn accurately from one waypoint to another. We also have the 298 motor controller that gives us speed control to both of our motor encoders, and our transceiver is to communicate between Peter and its controller. We also have the SparkFun Hall effect sensors as our backup encoders for our 2 motors that has the encoders built in. So right here is our PID system. It's our closed loop for when Peter is turning. So when we want Peter to turn from one waypoint to another, we get the degrees that he wants. So say he wants to turn in 90 degrees, this PID right here will ensure that he will turn an accurate 90 degrees. So basically our target position on the screen here going to the controller is our turning degrees, and the equation below it is our PID equation that we use inside the code. U of t is our controller signal that we send to our motor controller. Basically, the U of t is the amount of current that we send to the motor controller, and it basically tells how fast the motor should turn. And this is in-depth continuations of our PID system. We have our integral equation as well as our derivative equation, and we have a little snippet of our code on how we were able to obtain those 2 values. We started out with Kp, Ki, Kd, our proportional integral and derivative values to be 1, 0, and 0. We found out it had a little overshoot to our target values, so we raised up the integral value by 0.025, and we were able to squash that overshoot and was able to turn to the accurate degree angle with no errors.
So just highlights on my end. Building the frame, it started in October with a plastic frame with the tank treads and stuff like that, and we eventually were moving it to aluminum for more rigidness, impact safety, and then better mounting just all the way around besides using plastic. We added the encoders, the GPS, and the compass to the framework for all the feedback data that was not 100% in our original design. And then we have as stated before, the custom built controller system.
And going based off of that, so we also included PCBs into Peter as well as the controller, more permanent design there as well as better conductivity. And then the PCB inside Peter is for the power rails. The plastic walls to protect the internal components on Peter, as you can see. As well as it's lightweight. You can also see in a bit with the lights as well that turn on inside there. And then the plastic 3D printed part, which is up top here, mounts the transceiver, the compass mast, and the GPS signal booster. Key results. So obtaining waypoints. Peter obtains the first waypoint and calls it the initial waypoint. This is also known in the code as the home location. User then moves Peter to the next waypoint. All waypoints are stored inside of a structured array, and it's important to note that the 100 here is basically meant to keep the dynamic array at a lower system memory. We also thought that 100 would be a sufficient amount of data points, waypoints, maximum allowed. And then here is basically just a visual representation of what I just described. So mapping gets activated from the controller, and then Peter obtains the first waypoint, sends it to the array, and then user moves Peter to the next waypoint. Now if you reach that 100 waypoints, then Peter will stop, and it will send the user a signal or a message basically saying, hey, you've reached your max, right? Whereas if you don't, you simply keep obtaining waypoints.
So here's another key results and data and this is from our GPS module. We were able to get our accurate coordinates inside Jacobetti. As you can see here, we were able to read multiple longitude and latitude numbers, and I just chose a random number from that list and put it online, and it was able to locate me at Jacobetti. And here is the running route flow chart. So basically, Peter would get the activation signal from the controller saying run route is on, and Peter would obtain if Peter's at its home location, he would be able to go forward to its next waypoint. If he's not, however, at his home location, he would move until that home location coordinate is met. And basically, Peter would just keep moving throughout all the coordinates until he's reached the last one, and would continuously keep doing that until the user stops him. And while he's going through all the waypoints, the obstacle avoidance system comes online, and if anything comes 0.3 meters between Peter and the ultrasonic sensor, Peter would stop. And if it's a static object, he would move around it. If it's a dynamic, he would just stop, pause for about 2-3 seconds, and then move forward again.
So on the note of our obstacle avoidance, as stated, 0.3 meters, it's about 1 foot away from the robot. It can clear multiple objects in a row, so if there's like rocks and stuff in the way, it can avoid one rock, avoid the other, picking the best route. And then it always runs at all times with the system on.
And here are some more key results and data from our mapping. We went to the PEEF and mapped out the gym. And basically, we started at the corner of the gym and went to the other corner, and went to the other corner and the other corner, just make a basic rectangular square. And we were able to plot that data from our serial cable into an Excel file and plot that chart onto a readable, somewhat graph. And obviously, as you can see, it's not the perfect rectangular due to probably not as accurate as coordinates as we would like to, but we were able to have Peter see what he was mapping and have him basically see what area he was in. And here's another data, more complex shape of his mapping system. This is Jacobetti. This is the road around Jacobetti. We just started at one point and we just started moving him around to the other points, or just around the roads, and have him collect all the waypoints. And basically we took all those waypoints, put them in an Excel file, and then charted it out. And this is the map that we got from Peter's data.
So for the business case and applicability, how does this design compare to its competitors? Well, we can move it right from various devices rather than just having one set device with it. Only 24% of the dynamic memory is used inside the Arduino, the microcontroller. And then also it adds to the autonomous industry. We attempted to essentially innovate with this as best as we could in a sense.
And then also for just some examples for future development, other things you could transfer to, maybe painting an area on a wall, automated farming, as well as like an automated example, basically anything that wants to travel a set path, right, that we can program out. And then, so in conclusions, some lessons learned. Previously, last semester, we got some great feedback. Basically just saying we were too ambitious. There were some things that we weren't able to implement. So ambition can be a good thing or a bad thing. Label the power rails. That was a big one. And then also just buy backups because better safe than sorry. Future development, more features. As mentioned previously, the battery indicator as well as how to tell Peter the width with a keypad. And then also to transfer it to other devices for various operations. And then lastly, so conclusions based on facts, closed loop systems are required for accuracy.
That's it. Any questions? Yeah.
How fast is he traveling on in general? Like when you're moving him, do you control the speed? Do you have a set
Yes.
maximum limit?
So when you're mapping out the area, I have a code where he ramps up the speed with the motor controller. So he starts at 0 miles per hour and then slowly ramps up to about, I haven't measured the speed, but in code, the maximum power I can give the motor controller is 255, which is maximum current given to the controllers. I didn't measure how fast that was. So that's how fast he is when he's mapping the area.
Have you thought about incorporating something so that like depending on the application that you'd use it for, the user could set like maybe only 50% of that speed if it's something.
Actually, yeah, we were one of the, what was it, last semester, a variable speed device. Basically, it'll just a turn knob to tell how fast you want the motors to spin. Yes, that was an idea that we had, but we didn't incorporate to our idea we have right now. But yeah, yeah.
So you showed him going on Jake Betty, how long did it take him to go around to Jake?
What was that?
You showed the map around the Jake Betty, how long did it take him to go around to Jake?
Go around to Jake?
Go around
Oh, how long did it take? Oh man, that was like, okay, so all the waypoints that you see here are all the stopping points that we had, and just kind of like turn in and then go again, turn in and go again. It was a while. It was a while. This is 30 minutes.
30 or 40 minutes of us just
following. And then he would lose. It was cloudy, and he would lose the GPS signal. So we would wait until the GPS signal would be gained again. And yeah, it took a while.
So, did you say 800-meter range?
Yes, confirmed 800-meter range on an open field.
Did you guys try that?
Yeah.
That's almost half a mile, right?
Yeah, and actually the transceivers are rated up to 2 miles.
Okay.
So we didn't find a field that was 2 miles long. So we found one that was about half a mile long, and we confirmed that. And it probably could have still went, to be honest. Yeah.
Do you guys test on any terrain to see if terrain would affect its ability to go from point to point and get off and say like plus or minus 2 degrees?
Yes, concrete is tough on tracks right now. The motor slips sometimes, so when he's turning, you can definitely see the track slipping, and that's probably because we have plastic tracks on him right now instead of rubber. And actually on grass, he's actually amazing on grass for some reason. I thought it would be the opposite from concrete and grass, but yes, right now concrete is his hardest traction.
So, let's say you wanted to use Peter to mow the lawn. Is it at the point where average layman could set it up and mow the lawn in a grid pattern going back and forth, or is that another step in the programming that you need to set?
Yes, actually with the help of Deanna, we have an algorithm for that mapping where it just goes to zigzag after you map out an area. We didn't get that far yet because we're still troubleshooting the route running, but we do have an idea on how to get that pattern going and have actually different patterns as well. As instead of a snake, maybe you want to go around and just keep going inside, and diagonal zigzags.
Or like on a baseball field where they go checkered pattern?
Yes, yeah. Dr. Ray. Oh, sorry.
What's that bump out there?
So this initial waypoint, that's where you guys park. And then, oh, I know, and then I'm trying to, We were trying to think that too when we charted this. So we were like, okay, so that is where they park, and we turned to left, and that's where that right turn was at that stop sign over there.
Yeah.
And then this is where, I think, yeah, this is student parking right here. No, this is the student parking, and this was that curve going into the student parking. But I believe he just.
Pretty sure he just lost signal.
He just lost it, yeah.
we had a solid like 11 minutes of just staring at the GPS, just a red light, no blink. Just like sitting there on the ground waiting for it to do something.
That's the nickel.
Can you go back to the slide with your PID code?
Yeah.
I hate to do this, but.
This one or this one?
Was this your actual code?
Yes, this is actually a snip of our. I mean, it doesn't have all the variables we have inside. Like right now, previous T is not seen in here. Previous T is long. That was a global variable. But yes, this was a snippet of our code.
But you have KI equals 0 there.
It's PI, it's not PID.
Well, it looks like it's PD.
No, that's a. Huh? That's okay. Wait,
Yeah.
what are you looking at?
It looks like it's a PD controller, not a PI controller.
Oh, because they'll have KP, KD, and KI.
Yeah.
So you wanted me to have KP, KI, and then KD?
Yes.
Oh. So I will change that. I will change that immediately.
Martin, did you have a question?
I did, yeah. So if you go to your map of the gym, so you said it's not exactly square. Was that because of inaccuracies of the device knowing where it's at, or was it you guys maybe not being as diligent in like picking an actual perfectly square grid where you put your waypoint?
Yes. The second option. We weren't. Peter's ability to go straight right now is still in the works. It's not a true straight. It looks like it's straight for about 30 seconds, but if you keep going straight for more than 30 seconds, you can kind of see him offsetting to the right, and that's what you see over here, on from the first waypoint to the second waypoint. Yes, that's also what we're trying to implement our PID into next, is when he's going straight. So he's truly going straight instead of offsetting a little bit.
So that's the truly, you think, the
Yeah.
shape that you mapped out?
Yeah.
So it's conservative, because it's always going a little bit to the right.
I guess, yeah.
Dr. Ray.
Shouldn't have stopped at the nickel.
Is it a magnetic compass?
Yes, it's a magnetometer. We're actually having, that's why we put it on a mast, because we were having a lot of troubles when it was inside the aluminum here.
Yeah.
We didn't think it would have enough trouble, but once the motors would start running, our readings would just go haywire on the compass, even after calibration. So.
Right. Close to the source is
Right.
going to give you a big problem. But also up here, with all the mineral deposits, a magnetic compass is not very, doesn't always work.
Not ideal.
Yeah, not ideal. But yeah, if you
Okay.
put a compass next to a running motor, it's not going to be good either.
Right, yeah. We learned that lesson.
So,
Yeah.
say you're gonna paint walls, how well does it go up down the walls?
Oh, well, so that is, oops. Future development of Peter. He will have arms on him, and he'll, actually the treads are so good, he can actually climb the walls up. And
It sounds like more like painting floors.
Parking lot striping would be cool.
Yeah.
That would be, yeah. And
Hammer us.
So I have one more.
Wait.
You guys said it has GPS, so
Yes.
do you always have to drive Peter to the next point and then log it, or could you just pick him up, carry him to the next one, and then set it?
I mean, we can. Right now in code, we have him, so if he's not moving forward and if he's standing still, he gets a waypoint. That's how we have it coded right now into him to obtain the waypoints. I guess technically you can, if you want, to just pick him up and have a controller move forward, make him think he's moving forward,
Got it.
and then walk to your designated location and just stop the controller, and he'll obtain that waypoint.
Okay.
In reality, we had it in my car this morning, and we drove from someone's house to the bar, just mapping data.
And we,
It
you
does
can
map
actually
data on
see,
the fly.
you can actually see the route we took to the 906 bar.
So you can have it bring you back from the bar.
Yes, you can. If you lost your way around, he can.
Put a leash on it and have it walk.
All right, nice job.
Thank you. Thank you. You guys want to grab the control? Hey Sam, you want to grab the controller?
Plug this in if you want to use the slide wheels. So just before I forget, Matthew and Stephen, they submitted their abstract for the Celebration of Student Success. It's on Thursday. They were accepted. They're presenting probably something very similar to this Tuesday at 2 p.m. over in the Jamrich.
Thursday?
Thursday or Tuesday?
I guess Thursday. It's been a long day. Thursday at 2. There's a free lunch too. So.
My name is Stephen Williamson. This is Matthew Bourne. Our senior project is an autonomous ice fishing system. This right here is the main system on the market today. It's called the Jawjacker. We were looking to improve on this by introducing electronics. This is a Michigan fishing law that most applies to systems of this type. The main thing that it states is that all lines must be under immediate control. And I would say in our system, we are under immediate control.
All right, so our original design did not work out as well as we had hoped. So we had to make a lot of changes from the beginning. As you can see from the beginning, we started with a PVC rod holder and a sliding mechanism, but that didn't really work at all because it was not holding the rod very stably, and it was just not really working that well. And also we were using a flex sensor at that time, which also was not a very accurate sensor at all. So then what happened is we moved on to our second design, which is basically using these kind of strap clamps. And it wasn't ideal because we wanted to be able to take out the rod whenever we wanted. We were still using the flex sensor at that time, but we decided to move on to our more final prototype, which was our second prototype, which used a strain gauge, which is extremely accurate, and it's great, it's perfect. And then we also used these broom clamps, a lot like something where you would hang up something on the wall with. And we also improved our reel to motor interface to allow for more torque as well, or easier torque basically. We then took our system out for fishing after our second design, and it was a huge success. Before I play the video, I was fishing and I only caught 2 fish. The Jawjacker that we had caught 0 fish. And this system here that we made caught 5 fish on its own. So here we go. As you can see, we are making it jig. This is something we added to help increase the action. Couple key things here is you can see that the
a reel-in speed in the beginning increases quickly when there's not a lot of tension on the rod, and it stops when it gets to a certain point. Something not highlighted in here is that it also can reel backwards if there's too much pressure on, which will allow for not using the drag system already integrated into the reel itself, and it will allow us to know when to stop exactly at the ice hole. And this is our results. These fish, we wanted 100% fish survivability, but unfortunately there is a 5 fish limit. So we did take our 5 fish per person. We also had a third person there. As you can see, there's more than 10 fish. So our system did catch its limit on its own. But it was for Steven, so there was no legal issues with that. Yeah.
All right, here's the design overview. We're using a 5 kilogram load cell, broom clamps to hold the rod in place. We have 5 push buttons, one for reeling in, one for reeling out, one to set the home position, one to start sensing, and then the power button. We also have 3 LEDs. We're using a 150 RPM motor with an encoder. We have a rod stabilizing piece, a handle that we built, and a battery plug-in port to allow the battery to be switched out in and out easily.
Okay, so looking into we have a lot of features on our device, and the reason, so you can see that it says the limiter. That's the name of our device. After our incredible day of fishing, we decided to call it the limiter because of how well it caught the limits. Because it made me question my fishing abilities, I have to say. So looking into it specifically, we have a rod stabilizer, down here. Basically what that's doing is under high loads, the rod would often slip out. So we use that to make sure that the rod would stay into the reel to motor interface. We also have the load cell right here, which it may seem like that will not get a lot of pressure, but it actually does because the rod is very bendy throughout the entire rod. And then looking on top of where our user interface is, we have our up and down buttons. We have our set home position, which we set to where the ice hole is to make sure that the fish doesn't come outside of the hole, because that can cause line breakages and losing the fish. And then we also have our start sensing button, which obviously once you're at the specific depth you want to fish, the sensor will start sensing for a bite. We also have 3 lights, which is one is indicating when the home position is set, one is for when it's jigging and it's when it's not jigging, and then the last light is for when it is sensing or fishing. We also have our names on there and our address to follow local rules. Continuing on, we have a nice handle that is just helpful to bring this system around. It's only 10 pounds, so it's really easy to move around from hole to hole. We have our battery plug-in port and our battery lock, which is basically just holding the battery in place so it doesn't fall out if the system falls over. We also have our electrical component box with all of our microcontrollers and other electrical stuff, and our battery. And obviously we have our broom clamps here as well.
So once we made it look all nice, we needed to still make sure it would perform like how it did before. The best way to test this, since we couldn't get outside, was just to stand up on the mezzanine. You can see we're going to set the home position and then reel it down to where we want to start sensing at. Yeah, there's nothing in there. And then some weight will be dropped into the bag. and then it'll reel up when Matthew pulls on it. It'll hard enough, it will let out some line. But eventually it'll bring it back up to the home position that we set. Right there. So last semester we set out some goals for our design specifications. We fell short on some of them, but we exceeded a lot of them as well. So for the weight of the system, our goal was 20 pounds. Our weight of the system is 10 pounds. It's also a lot smaller than we anticipated. We fell short on the battery life. We were aiming for 12 hours, but we ended up getting 4 hours. But we were continuously jigging for 4 hours.
So looking at our like what we were wanting to do, or our dates that we wanted to make, we were fairly close to, or we were within a couple days of our design, when we wanted our designs and prototypes to be done. We didn't really have any issues with timeliness. We started really early and got everything that we wanted to get done. Yep. And then, so looking at to our bill of materials, currently we're looking at $182 just for the system, or like just the components of the system. It doesn't include any of our labor costs, the rod and reel, or the battery. The reason why we don't include the rod and reel and battery is because we want this system to be something that you can buy in the store and you put your own rod and reel into it, as well as the battery is something that most boat fishermen have already, and they can easily plug in with our system. Oh, and then one of the things that we manufactured was our motor to reel interface, which is something that we 3D printed. And then looking into what we would want to make it into, we could cut costs with the microcontroller as well as the motor controller itself. So we would be looking at around the $140 range. And this is compared to, we want to compare this with the jaw jacker that has jigging. That is the full sale price currently of the jaw jacker with jigging. But the issue, or there's no issue. It doesn't do as much as ours, and ours has a lot more ability when it comes to catching fish and flexibility as well. And also our jigging is much better.
All right, here's our wiring diagram for the whole entire system. And then looking forward, we could add a full display to this. It'll allow the user to adjust the jigging and the weight sensitivity for the system. We can make the system 100% universal. We think that most rods would fit into the system, but I'm sure there's some that you could find that wouldn't fit. We could continue to decrease the material and production costs, patent the design, size down to better fit specifications. Like Matthew was saying, the motor driver and microcontroller. We could use a printed circuit board and build a wiring harness that'll allow for easy assembly.
And then obviously we would like to thank Kale for helping us weld some things that we need to be welded, and Joe, or Professor Ruthier. Yeah, okay. Sorry.
That's all good.
For letting us 3D print some things, and obviously Seth and the rest of the electrical department. We always are like super thankful for your help and obviously your guidance, especially because we're both EET students, so building a mechanical kind of system was not always the most intuitive to us, but I'm glad that we got through it. Yeah. any question? Oh, also, I would like to thank my dad. Actually, had thought of this idea originally. Not obviously this, but just the idea itself, and I'm very thankful that I was able to try make it. Yeah, that's what we have.
Questions? So your original intent was to be able to pick up the pole and fight the fish yourself?
Yes.
So is that still, does that work that way?
Yes, you can just basically, once you move this, the rod stabilizer, you can flip it down and grab it out. And then it's the same thing, just putting it back in, and then you have to make sure that the rod handle is in the motor reel interface, and then just flip this back. Sorry, it's not on right now, but yeah. And yeah, the most newer reels today have this thing called zero reverse, which allows for the reel to move forward and backward. And that's a design feature of these reels that we decided to exploit into a bigger, better product.
In your design specs and then your actual test, you said 100% fish survival rate?
Yes, so like I said, that day we were able to take fish, but all of the fish we could have taken straight from there and put it straight back in. As well as one of the main issues with the other systems is when it sets the hook on the fish and it's not like very loud and you can't really always hear it. And so oftentimes the fish will either swallow the bait or just sit there for a really long time and risk the fish dying. And with our system, if there's a hook set on the fish, it actually goes, and there's no fish on, the bait actually goes back to the original position, which is also another issue with this other systems. Is once the hook is set, you have to manually put it back. So.
What happened to your depth display on your first prototype?
Yeah. So what? Originally, we did have a depth display, but when you're fishing, you're pretty much always going to have a depth finder with you, and you can see the bait itself. And we were starting, at the end, we were starting to try to cut down costs to make this more marketable. And it wasn't a necessary feature as of now, I guess. But obviously a display would be something that we would definitely look into.
We just need to know how much line you can put out, right?
Right. Yeah, and we're using the motor encoder to tell us how far we have line up.
So if you had an LED display, you could
Yes.
show the depth.
Yes, and we had that running before, but we decided to not include it.
This is more of a comment, but it was really cool seeing when I got to work every day that I knew the two of you were gonna see sitting on the workbench. And when I left at the end of the day, you two were still gonna be sitting at the workbench. It was really impressive how much time I put in that. You did a great job.
Thank you.
All right, nice job. Thank you all for coming. Thank you all for putting in so much effort, so much yourselves into these projects and evidence as you do these presentations. Thank you to the folks who came and watched. And let's give their presenters another round of applause.